we have certain expectations associated with syntax that we have. And those expectations then give us further explanatory power. Here's what I mean. If you're deep in some code and you see f called on some parameters and you don't do anything with the return value, this is probably performing an action. It probably has some consequence to the outside world. It wrote to a file, it opened a socket, it closed something. It probably has some outside effect. Otherwise, you would have captured the return value. But here, you called the function but didn't capture the return value, so it probably did something. Whereas if you saw f and it returned a value, this probably performed some computation because you cared about the result and you're going to do something with the result later. If you're looking through some code and you see D with a square bracket after it and K and you assign that to V, this is probably a dictionary that's performing a lookup with a key giving the corresponding value. If you saw X's with a square bracket and a variable called index or maybe a variable called I and it returned a value, this is probably a list that's looking up an index and returning a single element. If you saw object.a and it returned a value, this is probably doing an attribute lookup and it's returning whatever was at that attribute. Note, these expectations guide our behavior, but they may only very loosely hold. Because if you see v equals d of k, this probably is a dictionary, but it might not be. It might be a default dictionary, or it might be a counter, or it might be a chain map, or it might be an ordered dictionary. But note that even though this isn't strictly a dictionary, knowing that it probably is a dictionary, that loose expectation is actually enough to guide our behavior because in this particular case, it doesn't actually matter which of these four types it is. We should largely be able to understand what this line does, irrespective of which of these types it happens to be. There are other expectations we might have. When we see any one of these syntactical forms, we might intuitively say, that's fast. I'm not going to do d of k, and it's going to take me 2 minutes to get a result. And if it does, I think something has gone wrong. I'm going to double check that I haven't done something wrong. Whereas if I call a function could be fast or it could be slow. I really have no expectation, which means that implementing the behavior as a function does not give explanatory guidance. It is absolutely the case that we could have written this class to be very time-consuming operation on a get item, but probably somebody is going to really wonder what's going on if they do a square bracket lookup, and it takes a long time to give you an answer. When we see each one of these forms, we typically think these forms are pure, they're stateless, they're not going to change the object itself, they're not going to change the outside world. That would be pretty bizarre. And we'd expect that their result is really going to be based on the state of this object and whatever key we pass in. Whereas when we call a function, we have no idea. This thing could maybe make a change to the outside world. This thing could be relying on some data that you can't see. Now, note, this is not the case even with common things like a default dictionary. Note, when you perform a lookup on a default dictionary, it does in fact mutate the default dictionary if the key existed, but that expectation is still something we rely on because it doesn't actually matter, irrespective of whether the default dictionary does or doesn't mutate itself on lookup of an entry that doesn't exist. The thing behaves the same no matter what. Now, when we look at code like this, we have certain expectations that guide our behavior, that give some explanatory power to our code. Namely, when we see this, we expect there could be an index error if we're out of bounds. And that's something that'll happen under normal operation. When we see this, we might say, okay, there could be a key error under normal operation if we looked up a key that doesn't exist. When we see this, we might say, well, there could be an attribute error, but something has gone really wrong if we looked up an attribute and we got an error, an attribute error. We don't usually check for attribute error. Whereas when we see a function, we really have no guidance. We have no additional explanatory expectations. Anything could happen. This could raise an index error, a key error, an attribute error, a runtime error, a file not found error, a module not found error. And when you look at some code and you see this, you say, oh yeah, they were worried that maybe that key didn't exist. Completely normal. But if you saw some code like this, you'd be like, okay, wait, they probably ran into this problem deep into field testing of this code, and under some weird circumstances, the attribute didn't exist, but they didn't really expect it, and they probably added this after the fact, and something weird has happened here. You don't usually do try except for attribute error every time you do an attribute lookup. Oh my goodness, it would make your code so noisy. And if you saw some code like this, you'd be like, oh my goodness, how on earth did a dictionary lookup turn into a file not found error? That is absolutely the most bizarre thing. And so, when you are using libraries for the first time and you're sitting down and you're deciding, okay, I'm going to write this. Do I put this in a try except? you have reasonable expectations that guide your behavior that, okay, I do if I'm worried that this key may not exist, but if I'm not worried about that, I don't. You almost certainly won't write every single line of code like this because you'd never be able to get anything done. These expectations give you explanatory power and guide your behavior in effective ways as long as they mostly hold. Now, one other thing to note is, for these three behaviors, there is no additional modality associated. You can't add a keyword argument to any one of these syntaxes. The grammar doesn't support it. There was, in fact, a PEP to try and add keyword arguments to these syntaxes here, but it wasn't accepted, and at least at the current day, you cannot add modalities. What that means is, when you see any one of these in code, you never have to think, oh, did somebody forget a keyword argument? Is there supposed to be a modality here? Is there supposed to be a flag that I need to pass to make this work correctly? Whereas when you see this, you get no guidance. You have no idea. Oh, maybe I need to look at the help of this and see if there's a keyword argument that I have. When was the last time you imported something from some module and you did a help on t.getItem? You don't, because it can only behave in a certain way. It's very constrained. There are ways to encode modalities in these different syntaxes, but there's no way to encode them directly in the syntax itself. In other words, if you had a modal parameter that you wanted to add to a function, you would encode the modality by just adding a keyword argument, meaning you have made this function more complex. Somebody's going to have to write a help of f to really get a sense for what this function does. But things like a pandas series do have modalities. The lookup is in fact a modality. You can look up based off the position or based off of the index. And we can encode this modality. We just can't encode it as a keyword argument. We encode it via the descriptor protocol. Or we encode it via some sort of aggregate object that we pass in, which is generally too clumsy, so people don't usually do this, but you'll see this in things like xArray. You can pass in for the selectors, you can pass in a dictionary that allows you to pass in modalities. Or you encode this modality by writing a function that returns something that performs some modality or gives you different results based on that modality. Or you use a nominal decomposition, so you have multiple properties and you choose which of these properties you want in order to get the mode that you want. Or you do something like what pandas does and you have descriptors and you choose via this nominal decomposition which of the descriptors you want, the lock or the iLock, the cell or the iCell if you're in something like xArray, and you choose which of those modes you want, but you can't encode the modality directly in the syntax, which means the syntax has a very tight expectation around what it does, and it can't do anything more. It is very good guidance for somebody. Here, the other thing you could maybe do is you can encode that modality, in the type itself, and then here you can see a common pattern. You set something, you unset something, so maybe you introduce another mechanism like a context manager to encode the modality. But fundamentally, in all of these cases, you're encoding that modality separated from the underlying syntax, meaning a user who's seeing their library for the first time, seeing this code for the first time, doesn't need to worry about those modalities existing. They're not going to do a help. Like when you do a help on read CSV and you see a million different possibilities and your head's spinning and you're not sure which of them you want. With these syntaxes, the user can only really do one thing and they have an expectation for what it's going to do. And they have a very strong expectation. And so it simplifies their onboarding for this tool. And when they need those modalities, they go somewhere else and look up those modalities separately when they're ready to do this. You can arrange the complexity of your library according to the sophistication of the user and how this user sophistication grows over time. Here is our conclusion. When we want to implement data model methods, we want to implement them where they improve understandability by leaning into the expectations that somebody has around these data model methods and maximizing the expectations that somebody can bring to this code.